In my talk, I will start with quantum measurement. So if we consider probing the position of a test mass continuously, okay? So this is a problem that Burginski started thinking about in the 1960s in connection with gravitational wave detection. So this is the early times. So if you think about there's an initial wave function for the test mass. And then you will make a measurement, and that will collapse the quantum state of this test mass to a new wave function, which is narrower and has a peak shifted from this original location. And then this narrower peak would evolve into a broader peak because of this momentum uncertainty here. So you can say, OK, but there is a position momentum uncertainty here. The more, if you say that, suppose I want to have a higher resolution at the first moment, I would have a finer resolution in position, but that would perturb my momentum, and that would cause a broadening of the wave packet, and that causes more noise in the second measurement. So with this argument, Burginski proposed that there is a so-called standard quantum limit for probing displacements continuously for a test mass. So fast forward, okay, in the modern times, when we consider laser interferometer gravitational wave detectors, this simple mechanism shows up in the noise spectrum of these detectors. Okay, so in the higher frequencies, we're limited by the so-called shot noise, the fact that we don't have enough photons to resolve the position. And in the low frequencies, we have the radiation pressure noise, where the photons kick the mirrors randomly and create this noise. Basically, shot noise represents this measurement error at the first stage, and the radiation pressure noise represents this momentum kick at the second stage. So when you trade off these two noises, you can say, let's put more laser power, and then you can have lower shot noise, but you're going to have more radiation pressure. On the other hand, if you lower your laser power, you're going to have a lower radiation pressure noise, but higher shot noise. So at the end, you have this trade-off, which does give rise to the standard quantum limit that Burginski, Caves, and Thorne worked on many years ago. And this standard quantum limit only depends on fundamental constants and fundamental parameters of your system, like the Planck's constant, mass of your mirror, and the length of your arm. So this standard quantum limit can be surpassed using quantum optics techniques, for example, by injecting squeezed vacuum, as Bill Unruh has studied and proposed in the 1980s. So the present day laser interferometer gravitational wave observatory, the LIGO detectors, use some of these quantum optics techniques and are very close to the limitation set forth by the Heisenberg Uncertainty Principle. So some of the more recent results, squeezed vacuum is used. Basically, so this is a schematic diagram of the LIGO interferometer. These are the arm cavities. And then the gravitational wave will change the differential arm length of the interferometer. And then the signal coming out here senses the position of the mirrors. And here from this port, you inject squeezed vacuum, which is the state of the electromagnetic field, which has either a very low amplitude uncertainty, but more phase uncertainty, or very low phase uncertainty, and but then therefore high amplitude uncertainty. So these are constrained by Heisenberg Uncertainty Principle. So depending on the frequency band at which you're looking at, whether either in the high frequency dominated by sensing a measurement noise, or you're at low frequency dominated by the back action, you correspondingly inject the right squeeze vacuum, and you can improve your sensitivity beyond the standard quantum limit. So this will be really providing more sensitivity towards observing gravitational waves from the universe. Here, this is one of the diagrams showing that, in fact, the quantum part of the noise is getting below the standard quantum limit. So this particular strategy of injecting squeezed vacuum to surpass the standard quantum limit was proposed by Bill in the 1980s. So LIGO is part of it's like one of these experiments which are called optomechanics experiments, where you use light or maybe microwave, electromagnetic field, to probe the positions of these mechanical objects to the extent that they're in the quantum regime. One of the kind of approach is to study levitated quantum objects, as Marcus Espenmeyer talked about. And so in this diagram, what I'm showing is that in these optomechanics devices, not only are you having a measurement sensitivity, which is below the naive constraint from the Heisenberg uncertainty, you can really witness the evolution of the quantum wave function of your macroscopic object in real time. So here, this is a quantum trajectory plot where the lines are basically where we think the center of the wave function is in the phase space. And these blobs are basically the uncertainty of your quantum uncertainty. And this is nearly the Heisenberg uncertainty. So basically, if I summarize this beginning intro part of my talk, what we really have right now is very good. We're able to use gravitational wave detectors to probe space-time geometry near black holes. And we're also able to use this, we're witnessing the macroscopic quantum objects moving in phase space according to Schrodinger equations. So, but then, I think since we're here, I'd like to say that we can have more bold experimental research into something to the more unknown regime. So I think there are two kinds, which I will try to talk about in this talk. I think the first one concerns whether there's a limitation toward how macroscopic the masses can be before they will not be quantum anymore, or they will be different from the predictions of Schrodinger equations, or quantum mechanics plus quantized gravity. And the second one is, are there additional space-time fluctuations due to quantum gravity that one can probe using these very precise, very sensitive displacement sensors? So let me focus on the first part. I think in the previous session, Bob and Dan both discussed the necessity for quantizing gravity. I think there's two parts, right? You have to, if you confirm that you quantize the near zone Newtonian gravity, then there's inevitable that you have to quantize the far zone field, because they're really connected. There's no way to separate them. And I think here I'm taking a different track. I think the loophole, as you will see at the end, is that this is not a unitary situation. Okay, but let's start from the beginning. Okay, so here I'm only going to talk about near zone Newtonian gravity, where we can say that the field operators are basically functions of the position operators of the particles you have. And therefore, at the end, the interaction between particles via Newtonian gravity is simply the Schrodinger equation. In your Schrodinger equation, you put in these potentials. And then, okay, so this is a statement that many experimentalists are pursuing at this moment. They would like to use experiments to show that you can transfer quantum information through near-zone Newtonian interaction, and therefore to prove that gravity is quantum. Okay, and then there was talks today that discusses the theoretical aspects of this. So I think today I would like to say, well, if we can prove theoretically that the gravity must be quantum, then there's no need to do any experiments. So we have to help climb up the hole to say that what if we have to think a little bit hard. Are there theories where gravity is classical? But then we have to be very cautious. If gravity is classical, then the so-called self-gravitating object, it just means that a system of particles whose motions are affected noticeably by gravity, their quantum evolution would have to be modified if gravity is in any sense classical. So I think, so this is just a side remark that gravity, in fact, is very weak interaction. So any of these experiments that are talking about using gravity to transfer quantum information, in reality, they need a very long time scale of quantum coherence to demonstrate. For example, if we have two objects interacting via gravity, we can see the shift. If we have already a mechanical oscillator made up of two objects, we can look at the shift of the eigenfrequency due to their mutual gravity. And that shift is this omega g squared over the omega 0, which is the original frequency. And the shift is actually, this omega g is very tiny, okay? It has to do with the density of the material. And for silicon, this is 63 microhertz. So it's very, very slow. So let's come back to this one way that people make gravity classical, which is the Schrödinger-Newton equation. So the way to do this is to say, well, I'm going to have a gravity potential, which is driven by the expectation value of my mass density operator. Okay? So at the one side, it's very interesting, okay? Because if you have a quantum self-gravity, you have this object, the gravity always follows the object. It's like, therefore, that object does not feel its own gravity, of course, except when it's accelerating, and then you radiate gravitational waves. But in the Newtonian regime, you don't feel your self-gravity. But if you have this Schrödinger-Newton equation, it actually does feel its own gravity, and therefore, it actually amplifies its own gravitational effect, which is experimentally a very attractive feature. But here the warning is that when you think about wave function to gravitate, it causes a physical effect. And there your wave function has to be part of the physical reality, whatever that means. And that causes a big problem today. Oh, that's right, because I didn't, There's the expectation value inside here. This is expectation value. This is a nonlinear quantum mechanics. So I first want to say, the good part of it, okay? So the fact that if you have self-gravity, if you have a mass made up from matter, which is very concentrated near the lattice point, which is how matter are made, the matter density near these lattice sites are actually much higher than the overall density of your mass. So therefore, if you actually compute this frequency shift, this self-interaction frequency due to this self-gravitation, okay, you actually add in this additional frequency shift, which much bigger than the naive gravitational frequency scale. Okay, I think this is what Birgitta mentioned on Monday when she talked about the CWL theory. This is actually the same mathematics here, but the physical context is a little bit different. So you can see that the frequency scale changes from by 100 times. Okay, so this is why we like to have this self-gravity. Of course, there are many problems with it. Okay, so the problem, well, let's focus on the good part for a minute when we go to the very complicated situation. So the good part is that if you do have this self-gravity due to this Schrödinger-Newton equation, you have this additional potential for the operator of the test mass around its mean value, okay? And when you have this situation, what happens is that if you write down the evolution of this wave function in the phase space, the mean value of your wave function evolves, of your quantum state, I guess, of x and p evolves with the original frequency that you observe from classical observation, but the quantum uncertainty actually has a different frequency because there's a restoring force coming from the self-gravity. This similar mechanism appears in the CWL theory, as Jordan would talk about, but that is between the different paths. Here, it's just within the same wave function. And so if you naively see, then you can say, well, this is very nice, because if you monitor the position of the test mass using light, you're going to have to see two peaks. The one peak happens when the thermal noise, classical thermal fluctuation drives your mirror, and that happens at the ordinary eigenfrequency of your oscillator. But the quantum noise, for example, due to radiation pressure, would have to be driven by this different frequency, okay? And the frequency is offset from the original one. So this is what you naively expect. If you look at this equation and you say, I'm just going to cancel, erase this expectation value for x. And a related proposal for testing quantum nature of gravity is this kind of optomechanical continuous test, where they say that, okay, if I have this cavity from the left, I use quantum radiation pressure to drive the motion of the left mirror. This motion is quantum, and therefore, if gravity is classical, this quantum motion will be taken expectation value, and therefore, the gravity will not sense this quantum motion, and therefore, gravity will not transfer the radiation pressure-induced motion from left to the right side. So it means that even though the left mirror is driven by laser light moving quantum mechanically, the mirror on the right would not be correlated. The position of the mirror on the right would not be correlated because a classical gravity cannot carry quantum information. Okay, so this is very interesting. So this is where the things look very interesting. You say, okay, if the Schrödinger-Newton is correct, and if I can think about this in this naive way, I will predict different signatures that experiments would probably rule out, but therefore I can say that gravity is definitely quantum. Okay, so, but then let's think a little bit, which have to do with the more difficult part of the wave function being part of the reality. Okay, so here I have this picture that I like very much, because in quantum mechanics, what you're supposed to have is every measurement branch would be corresponding to a different branch in the wave function of the universe. And if you take expectation value of this over the matter density, but aren't these people all going to feel the gravity of these other things? Okay, so that's fundamentally a problem. I think Don Page made this a little more precise, but same idea. So he did a thought experiment. He said, depending on whether I see this counter 1 or 2 click, I will personally place the ball on the up or down. And for example, I will form this wave function of the universe, where in the first component, Don Page, I think this is him, for those of you who know him, I guess, the ball is up, and in the second one, the ball is down, and therefore, if you don't take the collapse of the quantum state, if you maintain the strict coherence of wave function of the universe, as quantum mechanics mathematically requires, without collapse, then the gravity is not consistent with our experience. So you must make sure the gravity will depend on the result of measurement. And this had led Polchinski in the 1990s to say that, no, this is just well, on the one hand, you must reimpose the results of quantum measurement onto gravity, and on the other hand, this is not going to work. Because if you have if you have a measurement here, according to quantum mechanics, depending on the frame you're in, you're supposed to collapse the quantum state of everybody in the same time slice. This is terrible in two ways. The first way is that this is not Lorentz invariant, and the second way that this is going to cause a superluminal telecommunication, because you, the person at B here, for example, Bob, would feel that something happened here before light cone is able to reach him. So this is a big problem. I think this led most people to give up on the Schrödinger-Newton equation. So then, I I think there's a loophole. And this loophole is actually intimately related to what Dan and Bob were saying, that if you have a unitarity, then the gravity must be quantum. Okay, so here, as you will see, the solution, or not a solution, the construction here is not unitary. And it is not unitary because you have to make measurements, and the whole physics world is not unitary if you consider evolution and quantum measurement at the same time. Okay, so this is a very contrived model where gravity will depend on what measurements you or we are making. Okay, but this nevertheless seems to be a mathematical way to have a nonlinear quantum mechanics model which does not violate causality. The bad part is that it depends on what is being measured in the space-time. So here, let's think about what a quantum control system does. It has a so-called plant, which is your quantum system, and there's a controller which can be tuned in terms of its classical parameters. So if you have a measurement system, you can collapse the quantum state of the plant and controller, and you gain information about it, but you can filter your results and then feedback onto the controller in such a way that the Hamiltonian of your plant and your controller depending on the result of your measurement. But your result of your measurement depends on the quantum state of your system. Technically, it depends on the conditional quantum state, which is the state you perceive as the state based on the result of your record. So this system, as you can see, it is not linear in the sense that it doesn't follow superposition rules. Depending on if you give a superposition state at the beginning, the result is not a combination of the two independent results. So I would like to make or Bassam had made the connection to do it this way. Okay, so you can say that suppose the mechanism of Newtonian gravity is many actuators in the space-time, and all of these actuators, they will take information only from within the past light cone of each of them. And all of these guys, depending on what they have seen in their past light cone, they would assemble the gravity field consistent with the quantum state they perceive each. In some sense, basically, everybody who makes a measurement, or every mechanism that makes a measurement, would have the responsibility to report to these guys, and then make sure that they would actually implement the right gravity field. So if you have a mathematical model like this, it's going to have a gravity field that mimics it is a classical field because you're readjusting the parameters of your Hamiltonian. It is causal because everybody just reports into the light cone. And of course, there are fundamental questions like what is a measurement, and which is the question that Dan asked Bill the other day. So this question cannot be answered from this framework. Okay, and also, for any quantum information that is lost, not to a measurement but to a decoherence channel, how do we quantify what measurements are made? So there are some ambiguities here, but I think in principle it shows that a nonlinear quantum mechanics model can be made causal. Yes. Okay. So I'm going to take this model and reuse it for this optomechanical quantum trajectory, and show what is the consequence. Also, so this is a lot of equations, but the key here is that when you use this feedback model for classical gravity, when you write down this so-called stochastic evolution equations for your quantum mechanics, okay, the mean value of x and p, they evolve according to the non-gravitational, just the classical frequency of the oscillator. But the quantum part of everybody here, the noise part and how the uncertainty grows, they follow this shifted frequency, which is the original frequency squared plus this gravity Schrödinger-Newton frequency squared and square root. So basically, this means that the effect of this classical gravity doesn't really change the frequency of motion of your mass, but it does have a symptom of changing the uncertainty very slightly. And here I'm plotting a little bit the signatures in this kind of measurement. So if you are to measure the position of the test mass using the ordinary way, and you try to probe different quadratures of the outgoing field, which are amplitude phase modulations, what you will see is that there's only one peak at the mechanical resonance. And also the uncertainty, as depending on the phase of your measurement, there is a certain amount of squeezing here, anti-squeezing here. When you have, so the message is that if your Schrödinger-Newton frequency, which is this gravitational frequency scale, which is tens of millihertz for tungsten, okay, very low frequency, the change in the level of quantum fluctuations you detect will be substantial if this offset frequency is comparable to the mechanical frequency of your oscillator. So this really calls for mechanical experiments that takes place at very low frequencies. So then coming back to the very interesting part, which people were very enthusiastic about testing quantumness of gravity using this way, it turns out that previously we said, if we measure the amplitude modulation here, trying to see whether the quantum force here can drive the phase fluctuation in here, drive the position, it turns out to be still correlated, and to the exact amount, or almost exact amount, the quantum Newtonian gravity would predict. It is because from measuring the amplitude here, you can actually figure out where the mirror is. So therefore, gravity would readjust classically according to where the mirror is, according to the amplitude measurement you made. And then gravity, so therefore it means that so there are two possibilities, okay? If gravity does not account for the result of your measurement, so if the classical gravity does not account for the result of your measurement, then it's absurd. The many world would, you know. But then if gravity does account for the result of measurement, then your action of checking whether gravity has created correlations, that measurement you make will enter the classical gravity and then still cause some correlations. But of course, there's a fine detail here. Here, you're creating the correlation and searching for the correlation at the same time. If in other proposals where you're creating, where you prepare quantum state and test later, it may be, this effect may be less important. But I guess if I summarize this part, it's really saying is that gravity is, if you want to consider whether gravity is classical, well, if you want to make an experimental test of the quantum nature of gravity, you better entertain a little bit of what it means, what's otherwise. And then, but if you think about gravity as classical, you have to really think how the results of measurement has to enter the classical gravity, which is a very delicate issue. Okay, and finally, let me just say that there's another aspect of the research which I'm also involved in, which is to search for to search for space-time fluctuations that may appear at lab-scale experiments. So there is a recent experiment that started at Caltech, led by Lee McCullough. This is called the G-Quest, which actually uses the photon counting technique that Dan mentioned to improve its sensitivity. So here, the motivation, I can comment on the theoretical motivation, which is that what you want is, if you have these causal diamonds, which have the spatial size of the interferometer, of your interferometer, you would like the scale of the fluctuation to be geometric mean between the size of the causal diamond and Planck distance. So this can be motivated by thinking about if you have these gravitational shock waves on the side of the diamond, and therefore causing a random walk effect and accumulate up to this scale. At the moment, according to this theory, for two diamonds which are offset by a distance in time, which is comparable to the size of the diamond, should also have a comparable level of fluctuation. This part is not very clear how to work it out theoretically, at least to me. But so right now, we're using effective ways to generate these fluctuations and model how the interferometers are going to respond. Rana will talk more about this as well. So I think I will stop here. Thank you.
Thank you very much, Yanbei. I suggest we do it like the last time. If there are very burning questions that need to be immediately answered, we do one or two now. Otherwise, we have one more talk and then have a general discussion session. Oh, okay. Well, here, okay. This is a burning question.
So I would like you to clarify this point that there was this argument by Polchinski about superluminal communication, but Schrödinger-Newton gravity is a non-relativistic theory from the beginning. So, like, why on earth it shouldn't contain superluminal communication in the first place?
Oh, it is. You're saying it is non-relativistic. Therefore, in principle, yeah, I guess what, okay, I think even though here our analysis is non-relativistic, it just means that within the device it's non-relativistic. It doesn't preclude the situation where we take two devices far apart by thousands of kilometers, and then we make our experiment separated by a space-like separation. And in that case, this superluminal, in that case, the relativistic treatment reduces to the Newtonian treatment here and Newtonian treatment here. And therefore, if you're able to, and then there's nothing seems to account for this effect. So therefore, I feel like you would still ideally want to observe the causality even when the local physics is Newtonian.
But let's do it in the discussion.
Okay, very good. So it's a good start for the discussion session. So thank you very much, Yanbei.